All right, welcome back to Easy Math with Nick. Today we're on video number 13, and today's topic is discussing and finding of the row echelon form of a matrix. So, without further ado, I have nothing else to say. Let's begin. So, how do we know when a matrix is in row echelon form? Today's video is going to be very informal, so just using basic like visual cues is all we're going to be really tackling today. I'm not going to go through an exhaustive definition by any means. So I'll provide an example of a matrix in row echelon form. And the reason I'm discussing this today is because it's useful for an application and in Algebra 2 or pre-calculus. Depends on what those courses contain. They sometimes overlap, but regardless, as I was writing, this is a prime example of a matrix in row echelon form. Because if we look at our reading terms in each row, they form sort of a staircase pattern here, right? With zeros underneath them. This is indicative of a matrix in row echelon form. So it doesn't have to be a square matrix, right? This is a rectangular matrix. It's a 3 by 4. Unlike our previous video on matrices, when we were finding the inverse of a 3 by 3 matrix, it doesn't. Our matrix doesn't have. It has no requirement here. It doesn't have to be a square matrix. And when I say square, I mean that the rows, that the number of rows are the same as the number of columns, of course, right? So that is not a requirement here. So for a matrix to be in row echelon form, it's not contingent upon the number of rows or columns. So that's as close as we're going to get to like defining this in any way. So how is this useful though? Well, if we're familiar with how matrices represent systems of equations, this matrix could represent systems of equations 3x plus 4y plus 5z equals 6. Y plus 8z 9, 10y, 10z, equals 11. And this is a very useful format to be in for systems of equations because we can easily isolate z by dividing by 10 and then plug in z up here to solve for y. And then once we have y, plug y and z up here to solve for x, right? That is a process known as Gaussian elimination, which is typically covered in pre-calculus, and it's very useful to get the systems of equations into a format like this, where even without converting this back to a matrix, we could sort of see that staircase format there, right? So hopefully you picked up on that, and that's why this is a useful application outside of just being its own thing, right? I don't know what I was going for there, but hopefully you get the point where the point I was trying to make there, how this is applicable to systems of equations, and why it's important for our system of equations to be in that format if we're going for ease of use and solvability. Make it easier to solve, okay? That's what I meant to say. So let's start off with an example of a matrix not in row echelon form. So if we have the matrix, I know I'm very unoriginal with these, right? But so if we have this matrix, right, this is not in row echelon form. It is another 3 by 4 matrix, but it's not in row echelon form. So what you would have to do here is in order to get to this point where we can do Gaussian elimination, or like the Gaussian elimination scenario, you have to do what is known as linear combination, where I'd say take 2 times the second row and add that to the first row, right? If I want to do that, okay? I don't know why I would, but that's just an example, right? This is very similar to what we saw, another parallel here with, I don't know why I'm drawing that arrow there, but when we were finding the inverse of a 3 by 3 matrix before, we used this notation because it indicated a row operation, right? So it's 2 sides of the same coin, essentially, and that's really what I'm getting at here. When we're solving systems of equations or trying to get a matrix into a specific form, you do row operations or linear combination. There are essentially 2 different ways of referring to what's essentially the same thing. So to save your time here, I'm not going to be doing upwards of what I think I did 9 row operations in that video that took like 15-20 minutes, right? We're not doing that today. A big part of today is using the calculator to help us. So we're going to use the calculator to get this matrix into row echelon form to make it easier to solve. Before one of you in the comments says, oh, wouldn't it be more useful to put it in row reduced echelon form, right? Yes, it would be, but that's not the topic of today's video. That form is more useful in this scenario, but I'm assuming I just don't care about that today. So we're focusing on row echelon form strictly today. I'll cover that in a future video if I feel like it. So savage, right? Ooh, getting a little spicy here. Okay. Completely derailed. Let's go to our calculator. So first, in order for us to find the row echelon form of this matrix using our calculator, we need to first enter this into our calculator, right? So first we're going to have to do second, that's our first step, second x inverse. So the x inverse button, if you on a standard graphing calculator, TI-84 plus I'm using here because I'm fancy. I press the blue second button, and the little text above the matrix button, above the x inverse button says matrix. So I click on that, and now I get to a list of potential matrices that I can slot here. From A to Z, I'm assuming here. A to J, I lied. A to J. So I'm going to pick A here because that's the easiest. So we're under the names category though. So what we're going to have to do next is we're going to have to do 2 right arrows to decide to get to edit. And finally, we choose a letter. Choose a letter where we're going to slot our matrix into. If you have a lot of matrices in your calculator, you might choose a different letter than I do, but I'm going to choose A here because that's just what's obvious to me. So now, at this point, I'll continue down here. Enter your matrix. We're going to enter the matrix we have here. At the top, you'll be able to choose the number of rows and columns. It's rows by column, so I chose 3 rows and 4 columns. And now, now you enter each element in the matrix that you have there. So I just did that now. So great, we entered the matrix in the calculator, but that's only the first part of the battle here. We still need to find the row echelon form, right? So next we are going to do second mode. This helps us quit and get back to the main screen, which is very important. I'm sort of going through this very slowly because I know not everybody is adept at using calculators, so I'd rather be more safe than sorry. So now that we're back on the main screen of your calculator and you can see everything you did in the past days, all your history, now you're going to go back into that menu. So yes, is this redundant to write again? You might think so, but I disagree. So now second x inverse again so we can get back into that menu. Now once we're back here, we're going to do 1 arrow to the right now because we're going to do math. You should be in the math tab now. And we want to scroll all the way down until we see REF open parenthesis. So scroll all the way down till you see REF open parenthesis. This, if it isn't apparent, stands for row echelon form open parenthesis. So this helps us find the row echelon form of a matrix. So we're going to, once we get to this, we're going to press enter. And that gets us back to our main screen of the calculator. But this is the part where it's easy to get lost. You need to now go back to that menu one final time so you can select the matrix that you want. So finally, there's a lot of steps here, but it's kind of repetitive how you keep going back to this menu. So now you're going to do second x inverse for the final time, I assure you. You do second x inverse, and now you're back. Select your matrix. Now you're in the screen, the name screen, which is where you select your matrix. We're not editing it anymore, so don't go to the edit tab. We're selecting our matrix here. That was poorly written, but you get the point. I chose matrix A, that's the one I edited. And now finally we should be back on the main screen and press enter one final time. So a total of what, 16 steps here. But once we press enter, now we have our matrix in row echelon form. So great. The matrix that my calculator spat out at me is going to be the following. 1, 10 over 9, Is this nice? No. But it's going to have to do 11 over 9, which is what the calculator gives you gives you repeating decimals. But if you know that 1 over 9 is 1.1, I'm sorry, is 0.1111 repeating, point, you can just convert to fractions, which I think is easier here. That's what I'm doing. I forgot how to scroll to the side for a second. Okay, so it was a little bit of a hassle to scroll to the right here, but we're gonna have 12 over 9. And then in our second row we're gonna have 1, 2, 3. That's nice, right? In our final row we have all zeros. Yes, that is that is a little bit annoying, at least to me, because you want that last row to have two elements here, right? So then we could have z equals whatever, z equals a certain number, z equals a, and then you plug that a into our second row when we convert to a systems of equations, right? But yes, that's a little bit annoying. But all that means is we're going to have to do some row operations, whatever. But not whatever. Very linear combinations to get this into the right format. I don't know why I said whatever. So let's convert this into a systems of equations now. So at the top, we're going to have x plus 10 over 9, y plus 11 over 9, z equals 12 over 9. Don't worry, I will multiply both sides there by 9. I have the very strong urge to do that. For matrix to be in row echelon form, sometimes you'll see, I've got mixed opinions on this online, but when I was looking this up, because I wasn't quite sure either. The leading terms in each row, do they have to be ones or not? The consensus I found, the general consensus is that they don't have to be. At least that's the first result I found on the good old Google. But the calculator gave us ones in both of those rows as our leading term, so maybe they do. But like I said, today is not an exhaustive definition type video, not very informal, as I'll say again. So let's continue. So now with our second row here, oops, I want to go back to black. Plus 2z equals 3. So let's multiply the top row by 3. I'm sorry, by 9. Oops. So we're going to have, I wrote 3. 9x plus 10y plus 11z equals 12. Wow, that's nice, right? And then the second row, we're going to have, we'll just carry it over. Okay, isn't that nice? Now we want to let's get rid of our y variables. So we're gonna designate this as row 1, designate this as row 2. Essentially like we're dealing with a matrix here, right? Because I'll say it again, linear combination and row operations are just sort of like two sides of the same coin, right? So we're going to do negative 10 times row 2 plus row 1. If you sat through the entire video where we found the inverse of a 3x3 matrix, you'll be very familiar with row operations and how long they could take. But I assure you, we're only going to be doing 3 in this video. I know, 3 exactly. So let's continue here. By doing this, we're going to get first row operation. I'll circle it. Next, the y's cancel. That's the whole point of doing this, right? Plus z equals 12 minus 30, negative 18. Yes, that is right. Okay, that's great. We got a starting point here, but now we want to have another expression that's in terms of x and z. So now we are going to do our next row operation. Minus 1 over 10 y. I'm sorry, row 1. Plus row 2. Let me make sure this is what we want to be doing, and that does look right. Okay. Yes. Okay, let's continue. This is our second row operation. I told you we're only doing 3 today, so we're almost done already. Okay, so it's going to be negative 9 over 10x, because there's no x term in the second row. So we're just adding that to nothing. The y's cancel, as intended. This is the hardest part of calculation here. Minus 11 over 10 plus 2. So minus 11 over 10 plus 20 over 10. Minus 19 over 10. I think that's right. No, I think it's minus 9 over 10. I think that's what I meant to say. Yes, because we're going to have, yes, Yes, minus, oh wait, minus 2 over 10 plus, oh wait, was I doing this? Was I checking? No, I think I got lost. I think I'm lost. No. Yeah, what am I, what am I doing? What am I doing? Um, yes, we're going to have minus 11 over 10 plus minus 11 over 10 plus 2, so that's 20 over 10. So minus 11 over 10 plus 20, so that's going to be minus 9 over 10. No, it's going to be positive 9 over 10. That was our issue. Okay, z equals, now we're going to have minus 12 over 10 plus 3. So minus 12 over 10 plus 30 over 10. That is going to be 18 over 10. Okay, just to simplify this, I'm just going to pull out a 9 over 10. Negative 9 over 10 to be exact. X minus z equals 18 over 10. If I multiply both sides by 10 and divide by negative 9, we're going to have x minus z equals negative 2. That looks like a negative z. Whew, good gravy. Negative 2. That still looks like a z, but that's a 2, I assure you. So now we have two expressions involving x and z. Let's go to town. So this is our new row 1, new row 2, whatever. I'm just giving those names. So row 1 plus row 2. That doesn't get easier than that. And I'll circle this in red again. Okay, this is our third row operation. I don't even know if this counts as a row operation. Linear combination, whatever. The z terms cancel just out of sheer coincidence, which is sweet. And we get x equals negative 2. All right, so now that we have that, we can plug this into here, and we'll get negative 2 minus z equals negative 2. Wow, they're really testing my skills here. So z equals 0, question mark. That's still valid. That goes with everything we have so far. So that's still right. But now we want to find y. So our original thingamajig, our original could go by this statement up here. Y plus 2z equals 3. We could plug it into any statement and it'll be valid. So y equals 3 because z 0. All right, so if we wanted to put this in the form of a coordinate, if we're looking on our like 3 axes here, that is our answer. But let's check if this is right? I could have made a mistake. I am human. I've made mistakes before. So let's plug this back in to our original matrix here, right? This, if you remember, can be rewritten as a systems of equations, right? 3z equals 4. So that's just our first row, right? So let's test our what we have here. So we had x equals negative 2, y equals 3, z equals 0. So x equals negative 2 plus 2 times 3, 6, plus 0, those equal 4. So at least with our first row, we're correct, right? So first row, correct. I'll put a check mark next to it. But now let's test our second row. So 5x plus 6y plus 7z equals 8. Now we want to test this row, right? What was our x? Short-term memory. Negative 2, 0. Negative 2, 3, 0. So negative 2, where are we? Got lost. Negative 2 times 5, negative 10. Y was, I can't remember, it was 2 seconds ago. Plus 18 plus 0 does equal 8. So our row 2 is good. Check mark. Good job. Yeah, nice little happy star sticker. Finally, let's check our row 3. Our row 3 can be converted to 9x plus 10y plus 11 z equals 12. X, I'll keep looking because x is negative 2, so we'll have negative 18. Remember, y equals 3, 30, plus 0, because z is 0, equals 12, and that is valid. So we found the correct coordinates, values for each variable. So there you go. We solved it. So essentially, by converting the matrix into row echelon form, it doesn't change any of the solutions, right? because just like in other scenarios, without even involving matrices, doing linear combination doesn't change your solutions, right? Of course it doesn't, because that's the way you solve multivariate systems of equations, right? But yes, but in this case, we're dealing with matrices, but it's still the same idea. Like that whole thing, two sides of the same coin. Linear combination, row operation, same thing, right? Two sides of the same coin. I'll say that for the third and final time today. And by with our help of Mr. Calculator, we were able to essentially make this kind of daunting matrix that we started off with here into into a more palatable form, right? In a form in which we can more easily exact the solutions when we convert that to a systems of equations. And so I think that's all I wanted to cover today. This does look like a lot of steps if we're looking at everything I circled here when we put this in our calculator, but half of the steps here are just second x inverse, right? You do that, what, 3 times? No, 4 times even. Oh my gosh, right? Um, I'm sorry, no, you do that 3 times. Yes, but it's really not difficult to find that in the menus of your calculator. It's hidden there, but it's a little bit hidden, but not too hidden, in my opinion. But that's all I wanted to cover today. It was not a very exhaustive definition of what row echelon form is. This is not a linear algebra video. It's mainly an application for pre-calculus and algebra 2. So if you ever see an exam question, given you have a calculator, of course. If you don't, it might not be advantageous because row operations can take a lot of time. But if you're given a calculator and you have a systems of equations with 3 variables like this, like we started with that matrix there, you could convert it to a matrix and then go in your calculator and ask to convert to row echelon form. And oftentimes that'll help you solve very easily and get you into that format where you could do, like we saw here, Gaussian elimination, where we can solve for z easily, then plug that z into row 2 to solve for y, and then plug y and z into that first row to solve for x, and there you go, right? That's very nice and satisfying when it pays, and it pays off very well. But I think it's if you don't have a calculator, it still could be more tedious than just solving for just doing linear combination traditionally, and not worrying about getting into row echelon form. It still could be advantageous, but it's really up to the student to make that decision what's the best way to budget their time. And as I said before, putting a matrix into row reduced echelon form can often be a better route if you want to get directly to the answer. But I'm not covering that in today's video, as stated before. So without, in fear of repeating myself, I think I'll end it here. So thank you for sticking by with me through this pretty decently long video. It's 8:51 where I am, sort of getting late. So I think I covered everything I wanted to. I didn't make any mistakes. Checked all my work. So yes, even and the one final thing I wanted to say here, while you're still awake, in our last matrix that we had here, when we asked our calculator to convert it into row echelon form, it gave us the bottom row with all zeros. That's something that can happen, but we can still see that staircase pattern, right? So that's still indicative that we're in row echelon form. The leading terms there were ones, which I think is a requirement for row reduced echelon form, but I didn't think it was for row echelon form. Important distinction there. They're completely different, but have similar names. But I think it might be a requirement. But I said before, that's sort of a dispute, I think, online. At least I got conflicting answers on that. So enlighten me in the comments. I ask you to enlighten me there, whether I could have explained that maybe better, or maybe I could have, maybe I'm wrong. That's what I meant to say. Maybe I'm wrong about that. But some websites I found online said conflicting things. So you can't trust what you see on the internet, right? That's the lesson of the day. Take away something from this video. I meant to say, if you take away something from this video, take away the fact that the internet is not always reliable, especially AI-related things. That's a topic for another day, though. I think I'm going on a little bit too long here. Thank you for watching. My next video will be on calculus. I think I'll cover some FR free response question from the AP Calculus exam this year. as I know some students had trouble with. I think it was the non-calculator section, or maybe it was the calculator section. I'll see. I'll keep you posted on that. That should be coming this week. So see you then, and thank you for watching. Thank you.